Okay, today's lesson, integrals as net change. There'll be some nice review of how integrals work in the middle of all this, but as applied to net change, whatever that means. Well, we'll definitely get to all that. So recall that our exploration of integrals stem from problems involving motion. Initially, when we worked at integration, we used motion to motivate it because motion was something that we could easily talk about and put into application terms. Specifically, we saw that the area under a velocity curve gives us the distance traveled. Let me just highlight that as a review of what we've covered in integration before. If we want to look at each one of these little sections and say, okay, well, there's a little rectangle, and we did parallelograms, and we did trapezoids, and we did all these things, but if we just look at one little section like that, what is that little area represented by? Well, it's the velocity is the height, and the time is the width. And so each of those little rectangles means velocity times time, and velocity times time is distance. So when we're finding that area under the curve, we're actually taking whatever the y-axis is and multiplying it by whatever the x-axis is a bunch of times, all those little rectangles, and adding them all up. So that area under a velocity curve gives us distance traveled. Now, if the velocity graph was a horizontal line, the area is easy to calculate, and it's simply the area of a single rectangle. If the velocity graph is curved, we had all sorts of options here. We used Riemann sums. We used LRAM and MRAM and RRAM to do these things, and we often had our calculator to bail us out. And we had the trapezoidal rule and Simpson's rule. And if those things have dropped back into your memory a little bit, that's okay. I'll review them as we come up to them. And we use those things to estimate the area of the curve. Now, the limits of Riemann sums leads us to an integral, which allows us to accurately calculate the area under the curve using antiderivatives. That was the big breakthrough, was that we could use antiderivatives to evaluate these things, and some review of that coming up. So we will soon apply our knowledge of Riemann sums and integrals to a variety of real-world situations, but let's first revisit the modeling and solving problems involving motion. Let's just go back to those motion-type problems and make sure we're clear on how it all works again. So this question says the initial position of a particle is 9 centimeters. So it's 9 centimeters from something to start off with. Then the particle's velocity is given by v at t equals t squared minus 8 over bracket t plus 1 squared. Now what does the Riemann sum sigma v tk delta t represent? Well, let me draw a little picture of what's happening here. And I don't know. I mean, you could get your graphing calculator out and draw a nice curve of this thing, but I'm not really hung up in exactly what this curve looks like. It has some kind of shape to it. And what we're doing is we're taking a certain rectangle and we say, okay, we're going to use a point here in this trapezoid or rectangle. If we set the limit to make these delta TKs very small, they'd approach rectangles, but we did them with trapezoids as well. And we choose a point in there, and that's the TK. That's the point we're using to represent. And so this y value here is the velocity at the value we've chosen to evaluate to represent that rectangle. And what we found is it doesn't matter whether you use LRAM, RRAM, or MRAM. That's only going to change how fast you get to your answer. Because as the number of gaps that you use goes to infinity, all the answers are going to approach each other. So we just have to choose something to represent. And that's what the V at TK is the y value you've used to represent the shape you're talking about. So then, this width here is delta t. So what's going on here? This is the area of one rectangle, and this sigma means add up all the rectangles. So I'm actually going to write a couple of lines here. This says sigma v at tk times delta t equals add up each rectangle. And what does that measure? Area under the curve. So you're going to add up all those rectangles and get the area under the curve. And in this case, what does that Riemann sum mean? That means net change in position. If you want, it's the displacement. It's how much this thing is moved. You've added up all the velocity times times, and each one of those velocity times time represents a displacement. And once you do all the rectangles, then you've got the net displacement, the net change. And that's why the title of this lesson is Net Change. This lesson really was inside other lessons, actually, but now we're pulling it together and really talking about it separately as a net change. Okay, so it says state a definite integral. Well, we were at the point where we were using integrals to do these things. So instead of the diagram I had above, is we say, okay, we want to go from some A to some B, and if we want to find that delta D, I'm going to call it that displacement, that change in displacement. What we want is the integral from A to B, which just means add up all those little rectangles of the velocity. So this is V dt. Well, in this case, actually, we know the equation. They gave us the equation for the velocity. Let me just copy it into here. T squared minus 8 over t plus 1 squared. So we're saying if you want to get that delta D, you've got to find the integral, the area under the curve of t squared minus 8 over t plus 1 squared dt from A to B, from whichever limits you want to go to. This question hasn't mentioned yet what limits to use. If you're worried about this 9, yeah, me too. We'll get to that 9 in just a minute. Coming right up. So some actual practice with integrals here. It says determine the particle's position at 1 second and at 5 seconds. So what I want to do here, first what I want to do here is open myself up a little space. There we go. So we want the particle's position. I'm just going to rotate to there. So at 1 second, at 5 seconds. So first of all, I'm going to call that part A and part B. So here we go, part A. I want to find the delta D this time, but from 0 to 1 second. How long did it travel from 0 to 1 seconds? And coming right up is your antiderivative practice here. So antiderivative of t squared. Okay, well, if it's antiderivative, I know it's got to be t cubed. But when I use t cubed, when I multiply by 3 out front, there's got to be something out there to make sure it comes back to coefficient 1, so I need a 1/3. This came out to t plus 1 to the negative 2. So I guess I need t plus 1 to the negative 1. And that negative is going to get multiplied out front, so I guess I need a positive 8 out here to make all that happen. That's just me playing around with antiderivatives to go, what do I need to get if I take these numbers, these powers, and reduce them by 1? What do I need to start with? Now, maybe you need to write this part here as 8 times t plus 1 to the negative 2. Maybe you need to write that out separately when you're thinking to remind yourself that that's a t plus 1 to the negative 2, so I got to start with a t plus 1 to the negative 1. That negative's going to pop out in front, and I still need that coefficient of 8. I'm going to write that, and I still need the limits of summation. I put a little line here and go 0 to 1. Lots of times the textbook doesn't do that. It just does a 0, 1 on the side of the brackets, and that's fine. And so that's the second part of finding these integrals is you've got to do two things. You've got to sub in the 1. Uh-oh. My screen's froze here for a second. Let's just see if it comes back. I'll just go out. Come back in. That seemed to unfreeze things. Okay. So now I got to sub in the 1. So what I get is in my first bracket 1/3 times 1 cubed plus 8 times 1 plus 1 to the negative 1. And from that I got to subtract when I sub in 0 into this thing, so I get 0 in the first part, and then plus 8. Let's see, 0 plus 1 is 1 to the power of negative 1 is still 1, so that doesn't do anything there. And so, let's see, in this first bracket, I get 1/3 plus 8 over 2, so that's a 4. Subtract an 8 there. And so from the first brackets, what do I get? 12 thirds, 13 thirds, subtract 24 thirds, negative 11 thirds. Okay, so that's the delta D. That's how much it's changed position. Well, that's not going to be enough to get the answer because this object started at, or this particle started at 9 centimeters, and now it's in a delta D of negative 11 thirds. So I need to write a little more here, something like, okay, well, then my new position is whatever it started at as 0, plus whatever the delta D is. There's multiple ways to write this out, but we basically got to get our starting position in there, and so it's 9 minus 11 thirds. So 9 is 27 thirds minus 11 thirds. I get 16 thirds centimeters. That was part A. Now, go over that all again in part B. Part B says, okay, we got to find the delta D, but this time they want to know from 0 to 5 seconds. T squared minus 8 over t plus 1 squared dt. Find that antiderivative, 1/3 t cubed plus 8 bracket t plus 1 negative 1. But this time from 0 to 5. So in the first brackets, I get 1/3, 5 cubed would be 125, so that's 125 thirds. Plus, when I put 5 in there, I get 5 plus 1 is 6, so it's 8 over 6. Ooh, I'm going to reduce that right to 4 thirds right now. Isn't that nice? And then I got to subtract. When I sub this 0 into this whole thing, I get 0 from that first term, second term, 8. Let's see, 0 plus 1 is 1. The negative 1 is 1. And 8 over 1 is 8. Okay, so good. So I get 129 thirds. Subtract 24 thirds, 105 thirds. Oh, isn't that nice? 35. So that's the delta D. That's how much it's moved. Net displacement. So then again, I got to do, well, S is whatever it starts at plus the delta D. So it started at 9, added 35, and I get an end position of 44 centimeters this time. Okay, next question. What does the Riemann sum sigma absolute value of V of tk delta t represent? Well, in this case, we're not doing positive and negatives here because it's going to find the absolute value on each one. And so it's not displacement we're talking about here. This would be total distance traveled. And if that isn't clear, a quick example, like when you, if you have a pedometer on your watch or something like that that counts steps, at the end of the day, it only counts positive numbers. It doesn't count whether you move forward or backward, so it's always going to be positive. We call that the distance you've traveled. But if you start off getting out of your bed in the morning and ending up back in your bed in the morning, your net displacement is 0. You haven't ended up going anywhere. You ended up right back where you started, so displacement comes out to 0 because displacement can have positives and negatives, and those things can cancel each other out. So this is total distance. Now it says use a calculator to determine the total distance traveled in the first 5 seconds. So there's different calculators or different websites will use this differently. Your textbook uses something called NINT, and NINT will be on some applications, some computer programs and so on will use that. If you're using a Casio calculator, well, you'll just type this in directly. Make sure you're in math mode, and what you'll type in is, okay, total distance traveled will be integral from 0 to 5. You'll need the absolute value symbol, which you can find in the catalog. You go to catalog and down to absolute value. As long as you're in math mode, make sure you're in math mode, and so you get these options. And then you go t squared minus 8 over t plus 1 squared dt. Now, if you type all that into your Casio calculator, play around, you need the catalog and you need to be in math mode. And when you're in math mode, you get those math options at the bottom of the screen, and you can scroll over and get integral and put those limits in there. You type that all in, I think you get 12265 over 288. Try that out and see if you get that answer. Comes out to 42.6 what are we working in here? Centimeters. Okay, so try that out in your calculator. We want to be able to use the technology, so figure out how that all goes. Okay, revisiting the first example here. I want to move this up a little bit. I moved that down earlier, and so I want it back up at the top of the screen there. Okay, perfect. Rid of that. It says, okay, the velocity of a particle moving along a horizontal axis is given by ds dt equals t squared minus 8 over t plus 1 squared. This looks like the exact same example here. The only thing they've done is they've changed it. Instead of calling it v at t, they called it ds dt. And it says use the indefinite integral. So what we mean by indefinite integral is we don't know the limits of summation. We're not saying from here to here or from there to there. We're just saying indefinite. And what I mean by that is we're starting out with ds dt equals t squared minus 8 over t plus 1 squared. And then to find that solution, to find s, we're finding the integral, no limits, of t squared minus 8 over t plus 1 squared. Well, finding the integral is mostly the same with an indefinite integral versus a definite integral. We just don't know the limits of summation. So when we do this, we get the 1/3 t cubed as before. We get the plus 8 bracket t plus 1 to the negative 1 as before. But now we get this plus c because we don't have the limits of integration. So we don't know what this constant of integration is. The good news in this question, though, is we know, and we did before, what the value was at time 0. And so we know when t equals 0, the s has got to come out to be 9. And so when I type in 0 here, I get 0 plus 8 plus c, and so I get a c value of 1. So now I've got a nice equation for s at t in this particular version of the question. T squared, not t squared, s at t will be the 1/3 t cubed plus 8. Well, I'm going to put 8 over t plus 1 this time instead of using that negative power, and then plus 1. How nice is that, that I've got a nice equation to use? See, in the other version of it, I found the total displacement, and then I had to add in right there. I had to deal with the s at 0 myself sort of manually, but this equation doesn't need any of that. It just says, okay, you sub in, now I've got the equation for it. You sub in the t, I'll give you the s. So you can, in question 2, it says, okay, find s at 1. And so I just go 1/3 times 1 cubed plus 8 over 1 plus 1 plus 1. And I get till it's at 1/3 plus 8 plus 1. Oh, 8 over 2. That's not a 8 over 2. That's not a 8. That's a 4. And so what I get here is 5 1/3, which is 16/3. And that's the same thing I got up here, which was 16/3 after I added that initial position in there. But this one does it all in there because we haven't done it to specific limits. We've just done it in general. We want a general equation. And the same with this. If I go s at 5 in that equation, I get 1/3 times 5 cubed plus 8 over 5 plus 1 plus 1. 125 thirds plus, oh, that's the 4/3 again, plus 1. 132 thirds. When I divide that, I get 44. Same as I did above. So it's just another way of looking at that question using indefinite integrals instead of definite integrals. Well, let's just summarize what we've got for our strategy then. If you're using modeling with integrals to do net change, what you're going to do is approximate what you've got with some kind of Riemann sum, a representative value multiplied by the width of the rectangle, which we're not really going to specify the width of the rectangle when we're doing these type of questions, because we're going to be heading right for writing a definite integral, which you see in number 2. Write a definite integral from a to b of f at x dx, where you've got your function for the situation plugged into there now, and then evaluate the integral numerically or with an antiderivative. Numerically, if we're stuck, we might have to use our calculator or LRAM or RRAM as we move along here. Maybe we'll need Simpson's rule trapezoidal rule, maybe those type of things, and we'll review those things as we go, but that's the basic strategy here. So we'll stick with a simple example to finish today off. Another reasonably simple example where nothing gets too crazy here. So it says a car is moving with initial velocity of 5 miles per hour at a rate of 2.8 t equals 2.4 t miles per hour per second. What a strange unit. And this is used sometimes where the speed is quite large, but the time values we're talking are quite small. So again, unless you're going into physics, don't worry too much about the units in this question because I'll just walk you through it and don't worry about that too much. But if you're in physics, try and follow what happens with the units here a little bit. So, is this car developing undergoing constant acceleration? No, it's got a variable in there. No, it's going to change with different values of t. It varies with t. What does the area under the acceleration graph mean? Well, if we were to draw an acceleration graph, what we'd have is something, and again, I can see what this graph's going to look like. For this type of thinking, you don't need to be able to draw the graph, but it's nice to be able to draw a to-scale graph, and this is a linear acceleration. So there's acceleration, there's time. So to be finding the area, we'd be taking acceleration and multiplying it by time, and acceleration multiplied by time is velocity. So here the area here represents net change in velocity. So it's adding up all the little velocity times, and all the little acceleration times. Each one of those little rectangles that we draw, or little triangles, or little trapezoids, whatever shape we want, each one has t along the side, along the bottom, acceleration along there. So each one has a little velocity, and so when you add them all up, you're adding up all the little velocities. It says use the acceleration to find the car's velocity after 8 seconds. All right, so let me redraw my acceleration graph because they want me to use the graph this time. And the equation is 2.4 t. What that means is this graph starts at a value of 0, 0, and then at 8 seconds, it's a straight line here, just a equals 2.4 t. It's going to have this value 8, 2.4 times 8. 2.4 times 8, because it says 2.4 t. So I punch it in my calculator, 2.4 times 8, and I get 19.2. Now it says, if I'm going to use this graph to do it, well, I'm just going to find the area under the curve. Like, no Riemann sums, no integrals, no nothing. I'm just finding the area under a curve that happens to be a simple triangle here, really going back to very basics here. And so if I want to find this area, I'm just doing base times height over 2. The base will be 8. The height will be 19.2 divided by 2. Let me punch that in. 8 times 19.2 divided by 2. 76.8. And what does that represent? That's the change in velocity. It's changed 76.8 miles per hour per second. Okay? Oh, sorry, miles per hour. Just miles per hour, not miles per hour per second. Miles per hour per second was the acceleration. We multiplied that by seconds and got miles per hour here now. So the delta V is miles per hour. But if we want the actual velocity at 8 seconds, we need the velocity at 0 seconds plus the delta V. And the velocity at 0 seconds, it started at 5 miles per hour, and we've got a delta V of 76.8. And so what I get is 81.8 miles per hour. That's the velocity at 8 seconds. It started off at 5 miles, and it's accelerated all the way out to 81.8. Okay, next question, create a Riemann sum. So for a Riemann sum, you can go anywhere you want. See, we're going to divide this into a whole bunch of trapezoids or rectangles or whatever we choose. And then the Riemann sum says, okay, so at some value of time, which we're going to call tk to represent this. And so right here, this will have some value tk, comma, acceleration at tk. And each one of these will be delta t wide. So our Riemann sum says each of these little rectangles, if we use rectangles, will be a at tk high, and we'll have a width of delta t. So what's our Riemann sum? Our Riemann sum is our delta v will be add up each one of those acceleration times time. So there's a Riemann sum to indicate this. So then when you want to state a definite integral, we go delta v will be integral from a to b. It says definite because it gave us an a and a b to use here of the a at t dt. What do we mean by that? In this case, they give us the equation. So a to b of 2.4t dt. See, they gave us the equation for acceleration there. So there's the definite integral to use, and it says use that integral to calculate the car's velocity after 8 seconds. So if we want to find the delta v here, I want to know how much has the velocity changed from 0 to 8 seconds. And so I got to find the antiderivative. Well, I guess I need a t squared on the 2.4t. And so I'm going to be multiplying 2 by whatever's out front to get 2.4, so I need a 1.2 out there. I'm evaluating that between 0 and 8 seconds. And so when I plug in 8, I get 1.2 times 64 minus 0. When I plug in 0, this delta v will be 1.2 times 64. I get 76.8. And again, that's the delta v. So same as we did above, is we have to go, okay, well, the velocity at 8 seconds will be the velocity at 0 seconds plus the delta v. They told us it was 5. I just figured out 76.8, so I get this 81.8 miles per hour. So that's doing it with an integral instead of just from the graph. And you might look at that and go, well, wouldn't you just use the graph here? Isn't that easier? And maybe it is, but we use integrals all the time because the integral will handle much more complicated equations. This was a nice simple triangle. As soon as it's not a simple triangle or rectangle, drawing the areas is going to be really, really difficult. We did that at the start of one chapter there, and we drew all these areas out, and it takes forever, and it's a crazy calculation. So next, it says create a definite integral to represent change in velocity from 0 to t. So if we want delta v from 0 to t, we want to come up with an equation for delta v. We want to specify the t at the start in this particular question. And so we'd be going 1.2. Well, I can't use t again here. So it just says use u as a dummy variable to go, okay, well, the velocity is 1.2 u du. So, 2.4 u. The 1.2 was in that last question there. Okay, so that's if you wanted to come up with an equation for delta v for any t value, and we'd have to use a different variable there for going from 0 to t. You can reverse these variables if you want and say, okay, well, we're going to go 0 to k, 2.4 t dt, if that makes more sense to you. The nice thing about using the t is the upper limit of summation here is our equation will come out to be t's eventually. The u's will get subbed into the u's, and the u's are just a dummy variable for that reason. So it says, then determine an equation for the car's velocity at time t. So to determine an equation, we need velocity at any time t will be whatever the velocity is at time 0 plus whatever the delta v is. So the velocity at time 0 was 5. Plus this integral we've just created, 0 to t, 2.4 u du. And if you're still confused about that u, let's watch what happens with the u and why we call it a dummy variable here, is it really is just a placeholder for doing this integration. So I do 5 plus, and then I got to take the antiderivative here. And so what I get is 2.4 u, so I need a u squared and a 1.2 up front, similar to what I did above, 1.2 u squared. And I want to evaluate that from 0 to t. And so I get 5 plus in my first brackets. I'm subbing in t. See, u was just a placeholder for what I'm going to sub into. It's just a dummy. It's just holding a spot for me, so it didn't matter what variable I used in there. And then minus when I sub in 0, I get 0. And so I get a velocity at time t, 5 plus 1.2 t squared. There's the velocity equation for any time. So when they don't give you specific times and you want a general equation, you use the indefinite integral here. Oh, sorry, you're using the definite integral here, but with a 0 and a t. Final question, determine the total distance traveled for the first 8 seconds. If we want the total distance traveled, let's first find the delta D, how much the displacement has changed. And to do that, we want integral from 0 to 8 of the velocity. And we know the velocity now. And so, antiderivative time, 5t plus 0.4t cubed, I think will do the job. And we want to evaluate that from 0 to 8. Good news here is subbing in 0 is not going to do anything, so I just need my first bracket, which would be 5 times 8 plus 0.4 times 8 cubed. Second bracket, just 0. You know, when you sub in 0 to each of those things, you happen to get 0 this time. So I get 40. Let me just take that back calculator. 5 times 8 plus 0.4 times 8 cubed. Five times 8 plus 0.4 times 8 cubed. 244.8. And this is the first time that weird unit they gave us at the start sort of gets to us here. Because it's delta D, and we've multiplied by only seconds here. See, this one, this velocity here was in miles per hour. And then if we're going to multiply that by seconds, what we get is 244.8 miles per hour times seconds. And again, this isn't done to even physics students very often, so don't get too wild about this. It's just the way this particular question was set up. And so that is in miles per hour seconds, which is not, we'd never do miles per hour seconds. So to convert this over, see right now it's miles per hour times seconds. We now want to multiply by hours per second. If we multiply by hours per second, that will get us back to a unit that makes more sense to us. So basically all we got to do is go from seconds to hours here. So it's 244.8 times 1 over 3600. And the delta D here is actually 0.068 miles now. See, the hours and the seconds will all cancel and I get miles. But again, that little details, if you're not going into physics, that's not really something you're going to face all the time. So, and if you are going into physics, just follow through on the measurement conversion there. So delta D is 0.068 miles there. Okay, this is going to take some practice, folks. Dig right in and go after this this homework, because a lot of this stuff needs practice. It's not much more than what we were doing before, but it may take a little work to brush all the rust off of that. Let me know if you have any questions, and have a great day.